Alright guys, in this video, we're talking about chapter 6, point estimation. Actually, we wouldn't talk too much about this section, this chapter. 6.1 is the only section we're gonna go over for this chapter. So we're only talking about some general concepts of point estimation. Let me pull out the marker. Now, first of all, let's take a look at the definition here. A point estimate of a parameter theta is a single number that can be regarded as a sensible value for theta. A point estimate is obtained by selecting a suitable statistic and computing its value from the given data sample. The selected statistic is called the point estimator of theta. So, which means the point estimate is a number and the point estimator is a statistic. So what does it mean? So if we want to, for example, if we want to estimate the population mean mu, so we usually use the simple mean x bar as the point estimator, because x bar is a statistic, right? And the value of x bar is the point estimate. Okay, once again, point estimator is a statistic, and the value of the statistic or the value of the point estimator is the point estimate. Once that's clear, let's take a look at this example here. I think that will make everything clear. An automobile manufacturer has developed a new type of bumper which is supposed to absorb impacts with less damage than previous bumpers. The manufacturer has used this bumper in a sequence of 25 controlled crashes against the wall, each at 10 miles per hour, using one of its compact car models. That x is equal to the number of crashes that result in no visible damage to the automobile. The parameter to be estimated is P, is the proportion of all such crashes that result in no damage. If x is observed to be x is equal to 15 and the most reasonable estimator and estimate. So based on the definition we went up here, we know that the point estimator is a statistic. So if we want to estimate the p here, of course the point estimator is going to be p hat, and it's going to be equal to x over n. Okay, so x is the frequency and n is the total. Okay, p hat is the point estimator, and of course the value of p hat is going to be the point estimate, x over n, which is 15 over 25, which is equal to 0.60. Okay, so this is pretty much exactly what we went over up here. The point estimator is a statistic. I mean the statistic corresponding to the parameter. For example, if you want to estimate the population mean, then the point estimator is going to be simple mean. If you want to estimate the population proportion, then point estimator is going to be the simple proportion. In this case, of course, the value of the simple proportion is the estimate. In other words, the value of the point estimator p hat is called the estimate. All right, I wish that makes sense to you. Once it does, let's take a look at the definition. Bias. A point estimator theta hat is said to be an unbiased estimator of theta if the expected value of theta hat is equal to the value of the parameter for every possible value of theta. If theta hat is not unbiased, then the difference, the expected value of theta hat minus theta, is called the bias of theta hat. So basically, if you want to identify if the point estimator biased or unbiased, what you need to do, you just need to find the expected value of the point estimator and see if the expected value is equal to the value of the parameter or not. If they're equal, then this point estimator is unbiased. If they're not equal, then this point estimator is biased. Okay? All right, there is a proposition here. When x is a binomial random variable with parameters n and p, the sample proportion p hat is equal to x over n is an unbiased estimator of p. Okay, so we're gonna prove this over here. Based on the definition, we know that if we want to see if p hat is unbiased or not, we need to say if the expected value of p hat is equal to the value of p or not. If they are equal, then p hat is unbiased. Now let's take a look at what is the expected value of p hat. We know p hat is equal to x over n, right? And then, based on the property of expected value, 1 over n is a constant number. We can pull it outside of the expectation here. So that would be equal to 1 over n times e of x. So since this is a binomial distribution, what's the expected value of binomial distribution? Is n times p. This two will be cancelled out, so this is equal to p. Now we have the expected value of p hat is equal to p, then we see that p hat is unbiased estimator of p. Alright, I wish this makes sense to you. Another proposition here, let x1, x2 through xn be a random sample from distribution with mean mu and a variance sigma squared. Then the estimator, the sample variance, you can call it sigma hat square or s square, so it's equal to this, is unbiased for estimating sigma square. So I wouldn't go over the proof over here, so you just need to remember that the sample variance is the unbiased estimator of the population variance. In other words, we're going to have the expected value of the sample variance is going to be equal to the population variance. Okay, so I wouldn't go over the proof over here because that's not the important thing we're going to talk about. Alright, there's another proposition. If x1, x2 through xn is a random sample from distribution with mean mu, then x bar is unbiased estimator of mu. If in addition the distribution is continuous and symmetric, then x tilde and any trimmed mean are also unbiased estimator of mu. So actually, what you need to remember here is, or what you need to understand over here is that x bar is the unbiased estimator of the population mean. So which means the expected value of x bar is equal to the population mean. I wouldn't go over the proof over here, okay? So basically, you just need to keep the idea in your mind. So based on what we went over here, the sample proportion is the unbiased estimator of the population proportion. And the sample variance is the unbiased estimator of the population variance. And the sample mean is the unbiased estimator of the population mean. Okay, now let's take a look at the very last proposition here. And sometimes, we know the distribution of x1 through xn, okay? And we want to find the distribution of x bar. Let's take a look at this proposition here. If x1, x2 through xn is a random sample from distribution with mean mu and standard deviation sigma, then x bar is distributed with mean mu sub x bar. This is the average of the x bar, okay? The mu sub x bar is equal to the population mean, and the standard deviation of x bar is going to be equal to the population standard deviation divided by square root of n. Now let's take a look at why. Okay, so first of all, we know that the mu sub x bar is equal to e of x bar, right? And we know that based on the definition of x bar, we know x bar is equal to sum of all x values divided by n. Okay, now based on the expectation of based on the property of expectation, we can pull off the 1 over n outside of expectation. And since it's summation, we know that e of x1 plus x2, that is equal to e of x1 plus e of x2, right? So that's the property of expectation. So that's why we can pull out the summation outside expectation as well. Once we have that, we know e of xi is always equal to, we know that e of xi is always equal to mu here, right? E of x is equal to mu, okay? And so e of xi is going to be equal to mu. Then we're going to have this whole thing is equal to 1 over n multiplied by the sum of mu here. Since mu is a constant number and we are adding mu n times, we're going to have n mu here from this summation. And then 1 over n times n mu is equal to mu. Now we have that e of x bar is equal to the population mean. So this proposition is very important because we're going to use it a lot in chapter 7 and chapter 8. Now, after the expected value of x bar, let's take a look at the standard deviation. Okay, the standard deviation of x bar, same thing. We know x bar is equal to sum of all x values divided by n, and based on the definition of the property of variance, we know that the variance of ax is equal to a squared times the variance of x, and that's why we have that. That's why we have that the 1 over n squared outside the summation here. Okay, that's coming from the property of the variance, and we also know the variance of x1 plus the x2 is equal to the variance of x1 plus the variance of x2, and that's why we have the summation outside of variance. Okay, that's why we have the summation outside of variance, and we know the variance of x is the sigma squared. So we're going to have that the v of xi is equal to sigma squared. Since sigma squared is constant number, so we're adding the sigma squared n times over here, then we're going to have n sigma squared. Okay, so then instead of the square root, we're going to have that this n is going to cancel out the square here, so it's going to be sigma squared over n, right? So if we take it outside the square root, we're going to have square root of sigma squared is equal to sigma here, and on the bottom we have square root of n. And then we're going to have that the standard deviation of x bar is going to be equal to sigma over square root of n. And of course, the variance of x bar is going to be equal to sigma squared over n. Okay? Of course, the sigma squared is the population standard deviation of population variance given in the problem. Okay, so I think the most important thing is the most important thing in this section is the proposition that we went over at last here. Okay, this proposition here is the most important thing in this section because we're gonna use it a lot in chapter 7 and chapter 8. And then you may want to know that just have this idea in your mind. The simple proportion is the unbiased estimator of the population proportion, and the simple standard deviation or simple variance is the unbiased estimator of the population variance, and the simple mean is the unbiased estimator of the population mean. Okay. And that's pretty much all about this section and all about chapter 6. In next video, we're going to into chapter 7. Okay?